Okay, good morning, everyone. Welcome back to class. Hope you guys are all doing well here. So we are down to our last couple of classes for the semester, last few classes. It's the 26th. It's week 15. Thursday, we have no class. Okay, it's Thanksgiving break. That actually starts tomorrow, so no classes for the rest of the week after today. Then week 16 will come back on Tuesday. We'll try to finish chapter 6. If we don't finish it on Tuesday, then we'll finish it on this Thursday. And hopefully we'll have a little time to review for the final on this Thursday. So, it depends. Sometimes we need a little extra time to finish chapter 6. So we'll see what happens. But I did, or I will, if I haven't yet, publish a review that I made for you for some online students. So you can use that online review that'll pop up on Canvas. And then let me show you a couple of other reviews. So I posted this a few days ago. The STEM centers at various campuses are going to have some review sessions for you guys. So if you are going to the South City campus frequently, there's one that they're going to have on Wednesday, December 4th from 1 to 3. And then if you're at the Redwood campus a lot or closer to that campus, they have 3 different reviews they're doing Monday, Tuesday, Wednesday on December 2, 3, and I think that's supposed to say 4 there. Okay, so plenty of opportunities there. I don't know if they're doing any online reviews right now, but anyway, so you have those. You've got the one I'm going to make, or that I'm going to post on Canvas, and then hopefully next Thursday we'll have some time to review as well. So there's some options there for you guys. Do you have any questions as we get going? Anything you want to go over? Anything from the homework? Anything at all that I can help you guys with? Okay, so yeah, my plan, I want to get that, so I finally did get the exams back from the testing center, so I'll hopefully have some time later this week to get them graded. If I don't this week, then definitely by Monday I'll have them up on Canvas. So you have some time to look at that 4th exam before the final. The final will be comprehensive. There are 17 problems on it, and it covers chapters 1 through 6. So the 6th chapter doesn't have its own midterm, but it will be covered on the final. Okay, so yeah, you have to study everything to be prepared for that final. And just like on the midterms, you can bring, one sheet of paper with notes on it, front and back. Okay. All right. So let me know if any other questions pop up as we go through this. So let's go back to what we're doing at the very end of class. We were talking about the correlation coefficient, and so we actually created our own data set. We were trying to see if so we're doing some social science or kind of social science exploration, really, and we're trying to see if the size of the family that somebody grows up in has some kind of influence on the size of the family they later have. And we said that based on our data set, there is a positive correlation. It was about 60%, 0.5899 correlation coefficient. Okay. So I wanted to do one more problem in the homework. It's just to kind of pad and supplement the lecture notes here a little bit. I'm going to jump over to problem 7 in 6.2. Just think it'll help you guys to see one more problem here. I think the lecture notes could probably use just one more problem. So let's go over to the homework. And again, this is 6.2, number 7. Just a little more practice with the correlation coefficient. So it's kind of an interesting problem here. They're looking at textbooks. Okay, so we have these college textbooks that are being sold, and they so the person collecting the data recorded the name of the author, the title, the Amazon selling price, and the Barnes and Noble selling price. Okay, and so we want to compute the correlation between the Amazon price and the Barnes & Noble price for the textbooks. So we would expect them to be positively correlated, but not exactly a perfect relationship. Um, so how would we do that? If we want to compute the correlation between these two prices, well, we need to use the correlation formula. Okay, so and I told you last time we're not actually going to be using the formula by hand. We'll be doing all of the correlation coefficient calculations in GeoGebra. So for this one, I'm going to highlight the whole data set. So what you can do is you can highlight it and then right click and go copy. Or if you know Control C, that's doing the same thing. Then we'll run over to GeoGebra and we open up the spreadsheet. Okay, and then I'm going to paste the data into there. So I can right click and hit paste, and it actually did quite a good job there of getting the relevant data in there. Okay, so we're only concerned with the last two columns. So I'm going to highlight those, and I'm going to go over to the columns here, and we're going to do a two-variable regression analysis. Each book has two numbers. It has a price on Amazon, and it has a price on Barnes & Noble. So we hit the two-variable regression analysis, and just as we were expecting, we see a linear, positive, pretty strong-looking correlation there. Okay, but as we discussed last time, you know, it's hard. It's pretty much impossible to guess what R is going to be with any sort of accuracy by just looking at a graph. You really do need to calculate the statistic, and it's easy with software. We just hit the sigma x, and there we go. There's our correlation, 0.93, and 0.93 is quite strong. It's close to 1. It's very close to 1. So those two prices are highly correlated, which makes sense. They're both online, so if you charge too much more than another website, people will just go to the other website. It's pretty easy to find the best price. So yeah, those prices have to stay pretty closely correlated, although not exact. Okay, so what do you guys think? That's how we work with the correlation coefficient, and that's what it's telling us is how strong and in what direction the relationship is. So if you're okay with that, let's continue on. The linear regression is actually a very, very complicated topic. There's so much that we can do with linear regression. There's entire textbooks written about linear regression. There's entire careers. Statisticians will spend their entire career working on new regression techniques. It's very useful, and so we have more to talk about, basically. All right, so we've got the linear correlation, and then the next step, we really do want to draw the line through the data. Okay, so we have our scatter plot, and then we need to have some kind of way of determining what the best line is for capturing the pattern in the data. Okay, so I need a little more space over here. So I'm going to run over to here and draw a few pictures for you guys. Well, just draw one picture with a few different possible lines. Okay, so let's say we have the following data set. Okay, so we have a scatter plot there, and it's a strong positive correlation. So I'm going to draw 3 lines, and I want you to tell me which one is the best, which one best captures kind of the spirit of the data, the trend, the relationship. Okay, so here we go. There's line A. Okay, and then let's see here. There's line B, and that didn't turn out super well. Let me try that again. Still not good. Sorry, let me try one more time. There we go. Okay, so I have A, we have B, and then C. Okay, so which one do you prefer? Which one best captures the trend of the data, A, B, or C? Well, let me just ask, will anybody vote for C here? Does anybody think that C is the best line here? If you think C is the best, um, I wouldn't like tell anybody. Right? C is obviously a terrible line here. Yeah, it's going in the wrong direction. It doesn't hit any of the points. It's just a terrible line. So some lines we can eliminate just because they're awful, right? But when it comes to A and B, I think reasonable people could differ, right? I think some people might look at that and say that A is better. Some people might look at that and say that B is better. Um, and there's other lines that are similar that we could probably draw in there if I were better at drawing a line. But do you see what I'm getting at? How do we decide what the best line is? Or does it really matter? I mean, could we just use both A and B, or just pick one? Well, there is a way of determining what the best line is. Okay, so there are criteria, or actually it's just one criterion that determines what the best line is. Okay, um, so you could just kind of eyeball it, right? You draw your best line and use that, but there are better ways of doing this, okay? And so the criterion is called the least squares regression criterion, okay? So we say that the best line is the line that minimizes the least squares value, okay? So the least squares is where we look at all of the residuals, okay? And we add up the squares of the residuals. That's called the squared residual sum. Okay, and the line that minimizes the sum of the squared residuals is the best line. Okay, so what does that mean exactly? Let's go back to the drawing board here and try to help you make sense of this. Okay, so let's draw another scatter plot here. Okay, and then we'll have our line going through it. Okay, so we talked about the residual last time. The residual is how much the line misses for a point. Okay, so if we look at this point here, the line was predicting this value on the line, but the point was above the line. Okay, we call that a residual, but it's also an error, right? And so if you look on the formula card, it uses E for error, but it's also the residual. And so let me draw in a line here. The length of the line represents the residual or the error for that point. Okay, so each point will have a residual. It'll have an error. So for this point here, this point is actually below the line. So the line over predicted for that point, right? Okay, so that's also a residual. And each point has a residual, right? You just draw a vertical line from the point to the line, okay? So each point will get some kind of residual, okay? If the point lies on the line, then the residual is simply 0, which is good. It worked very well for that point, right? So let's clean this up a little bit. And so these vertical lines represent the residuals. So if the line is a good line, will the residuals be large or small? What do you guys think? What is our goal? Do we want to have large residuals or small residuals? What do you guys think? Small. Perfect. Yeah. Yeah. We want those residuals to be as small as possible. Now, why then don't we just add up the residuals? Okay, so we have all these residuals, right? So we've got this one here, we've got this one here, this one, this one, this one, this one. Why don't we just add them up and find the sum of the residuals? Well, some of the residuals are negative and some are positive. Okay, so if you add up a bunch of positives and negatives, they tend to cancel each other out. So what we do is we square the residuals. Okay, so we're going to square the residuals. And that's why we call it the sum of the squared residuals. Okay, so if you look on the formula card, it's the sum of the squared residuals. So we take each of the residuals, we square them, and then we add up the squared residuals, and the line that minimizes that is the best line. Okay, so luckily there are formulas that come from calculus that automatically guarantee that we have the least squares regression line. Okay, now I'd like at this point to do a little bit more of an interactive investigation here. So you don't need to open up this website. You can if you'd like. But what it does is it helps us understand the sum of the squared residuals a little bit more. So you guys have seen this website a lot, right? We've got our coin flipping app there. What I want to look at is this correlation regression activity that they have. I think it's really, really well done. Okay, so we have a data set, and it's looking at the length of somebody's foot and their height. Okay, so is foot length and height, are these two variables correlated? Yes, right? Taller people tend to have longer feet and vice versa, right? It's not a perfect relationship, but there is some kind of positive relationship. We see that here. Okay, so here's what I want to do. I am going to create a line, and I want you to help me figure out, just kind of by eyeballing it, what the best line is. Okay, so so here's a line, and what we can do is actually turn on the residuals. Okay, so you see that? So this is a line. It's obviously a terrible line, and it's terrible because its distance from each of the points, or most of the points, is pretty large, right? Those residuals are large. So basically what we're going to do is we're going to play around with the slope and the y-intercept of the line until we have minimized those residuals. Okay, so this is obviously a terrible line. The residuals are really bad. Likewise, this is obviously a terrible line because the residuals are really large, right? So let's see here. So we need to have moderation here. We don't want to have it too high or too low, right? If it's too low or too high, it's not great. So maybe somewhere here in the middle. Okay, so that's good. So you guys tell me when to stop with the slope here. So I'm gonna, obviously going down is not good. We have some huge residuals there. So tell me when to stop. Tell me when you guys think those residuals are as small as they get. Okay, so I'm gonna go a little bit slow. Tell me, I'm just gonna take the liberty of bumping that up a little bit. Tell me when to stop rotating the line here. Okay, and we're just kind of eyeballing it. Maybe this is sort of hard to do in Zoom, but what do you guys think? Maybe about right there? Okay, thanks, Killian. Great. Yeah, I think that's about right. Okay, so there are some large residuals, but most of them are pretty small at this point. And so the other thing we can do is we can, by clicking this box here, it will actually show us the least squares regression line. Okay, so that red line is actually the objectively best line. Okay, why is that? Well, because it's residuals squared, its squared residuals sum is smaller than our line. We did pretty well, right? I'm not ashamed of that line. It's pretty close to the red line, but it's not perfect. Okay, so again, what is the criterion? Well, we want to make these residuals small, but we can't just add up residuals. We have to add squared residuals. So the next thing we can do here is actually square all of those residuals. Okay, so each residual is a one-dimensional line. When we square them, they actually become these squares. So I know it's kind of trippy at first. We have all of these squares. What we want to do is make these squares as small as possible. Okay, so if I go too high or too low, the squares become huge. If I go somewhere in the middle, and then we get the slope optimized, it's going to minimize those squares. Okay, so that's the idea. Okay, and so anyway, let's turn off our line and look at the best line. Okay, this is the best line, it truly does have the smallest sum of the squares. Okay, so how do they do it? Well, there's a formula that comes from calculus that tells us the slope and the intercept of the line. Okay, so there you go. Hopefully that helps you think about it. This is the criterion. The line that minimizes those squares is the best line. Okay, so let's actually try one of these. Okay, and I do love the notes, but it's another one where I kind of like to do a slightly different problem than we have in the notes. So hopefully it doesn't make your note taking too hard, but I'm going to move over to section 6.3, number 8 in the online homework. Okay, and then I promise I won't jump around too much more here today. So I'm going to go to the homework here, 6.3, number 8. I think it's just a slightly easier example than we have to start off with in the lecture notes. So I'm going to go down to question 8. Okay, so this, I'll just put this in the chat here. This is 6.3, number 8. And what we're doing is looking at the relationship between number of absences and the grade in the class. Okay, so every student will have two numbers, right? Every student, who gets a final grade in the class will have two numbers. They'll have the number of times they were absent, and then they'll have the final grade in the class, right? So, and they're both quantitative variables, so it's something that we might consider for a linear regression. Okay, so let's find that least squares regression equation. Okay, so how are we going to do that? Well, we're going to use software. Okay, GeoGebra has the equations for the slope and the y-intercept. So let's go over to GeoGebra. So to get to this, we need to get the data into the spreadsheet. So we hit the toggle, the 3 dots, and go over to the spreadsheet here. Okay, and then I'm going to paste the data into the spreadsheet. So I go right click and I hit paste, or if you know the control V technique, that also works. Okay, so notice I copy and pasted the data, and I do that as much as I can, and you should too. It's faster and typically leads to fewer mistakes. So in the first column, we have the number of absences. In the second column, we have the grade. Okay, and so to get going with the analysis, we highlight the data, then we go to two variable regression analysis, and there we go. We see pretty much what we expect, right? On average, students who miss more classes tend to do more, poorer than students who don't miss class or don't miss many classes, right? So there's always exceptions. It's not a perfect correlation, but it does appear to be a pretty strong correlation. Okay, so the way we proceed is by creating the scatter plot. Then we look for a linear trend. Okay, remember, most of the techniques of this chapter are designed for linear trends. And so I think, if you look at that, it's pretty obviously a linear trend, right? We don't see any obvious curvature here. We don't see an elbow or anything like that. So it's a linear trend. So the techniques here of this chapter will be relevant, okay? So that's good. Then we want to look at the correlation coefficient. Okay, so we can come over here to sigma x, and we see it's negative 0.9539. So that's pretty darn close to -1, right? It's not exactly, -1, but very close, right? So we would call this a very strong negative linear correlation, negative relationship between these two variables. Okay, coming to class is very important for doing well. Okay, so but that's, we've already talked about that. So what's new here? What's new is we're going to turn on the regression model now. Okay, so that's down here. So it says regression model. If you click on this, what it does is it has a drop-down menu of common regression methods. Okay, so if you enjoy this class and you want to take more stats classes, then in later stats classes you'll learn about all these different kinds of regression methods. I was telling you earlier that people spend, their entire careers working in regressions. It's very broad, and so anyway, um, the only one we're going to do in this class is the linear, right? So these other ones don't concern us. So we're going to go linear, and as soon as we do that, it creates the line. So what it does is it has the equations programmed in that will produce the guaranteed uh, the line that minimizes those squared residuals. So objectively speaking, this is the best linear equation, the best linear line, that the best graph for understanding the relationship between number of absences and final score in the class. Okay, and so it creates the graph, and then it also gives us the equation. Okay, so let's write that down. So we have our equation. It's negative 2.7161 plus 90.6509. Okay, and don't forget the x in there, x being the number of absences. Okay, and I think that makes sense. Absences, will probably be the explanatory variable here. Okay, so where are we? We're back here in the homework. Okay, so what is m? What is the slope? So it's negative 2.7161, and then the y-intercept here is 90.6509. Okay, good. So that alone is quite useful for us. We've always said we want to understand the relationship between two variables. Well, this is about as good as you can do, right? I mean, you can very, very precisely understand how the two variables are related to each other. Okay, so that equation is great, but we can actually go a little bit further. And what we're going to do here is interpret the two parameters. Okay, so when it comes to a straight line, there's two parameters. There's the slope and there's the intercept. Okay, and so with linear regression, we calculate the line, and then we take the slope and the y-intercept, and we can interpret the coefficients. Okay, the two parameters. Okay, so what we're going to do is interpret the slope, and then we'll also interpret the y-intercept. Okay, so let's go back to our data set here and do that. Okay, so we have, what do we have? We have this, let me do something here real quick. Okay, all right, so we're going to interpret this slope here real quick. So what is slope? You guys have studied algebra before, right? Slope is rise over run. Okay, so if you have a straight line, then between any 2 points, you can always draw a right triangle, right? So on the right triangle, we have run for the horizontal distance, and then for the vertical distance, we call that the rise. Okay, so slope is m, right? That's the letter we typically use, and it's rise over run. And in this case, for this problem, we noted that it was negative 2.7161. Okay, so I want to do an interpretation here of the slope. Okay, so to help us do that, I also want to practice with our equation a little bit. Okay, so we're going to practice here with the equation a little bit. So the equation that we got from GeoGebra was negative 2.7161 x plus 90.6509. So let's do three things. I want to use this equation to predict a few different y values. Okay, so let's predict the score for a student with 0 absences, with 3 absences, and with 4 absences. Okay, so I'll get us started. I'll do the one with 4 absences. Okay, so let's say we have a student who's had 4 absences. So we have our graph, and so if we just kind of want to quickly estimate, we can run over here to 4 and then go up to the line and then go back over here to the left. Does that make sense? So just kind of eyeballing it, it looks like a student with 4 absences would be predicted to score about an 80, maybe 81. Kind of hard to tell on this axis, but so just kind of estimating it quickly, I would say about 81%. Okay, but we can do better than that. We can use the equation. Okay, so the equation is y hat, and in place of x, I'm going to drop in 4. Okay, so if we want to know 4 absences, right, we'll put 4 in for x there, and then we'd run over to the calculator, and it's arithmetic, right? Not too bad. So we go 2.7161 negative times 4, and that's going to be negative 10.8644 plus 90.6509. Okay, so then I'm going to go plus 90.6509, and we have, so it's actually a little bit lower than my estimate by looking at the graph, right? So on average, we would expect a student with 4 absences to score around an 80%, okay? So I want you guys to do the other 2 values, okay? So, and let's keep it at 4 decimal places of accuracy for a very particular reason that we'll see in a little bit. So let me go quiet here, and I want you guys to try these other 2, okay? So this is very important. You'll have to do this on the exam. You'll put in various values for x, and then you'll use those to predict the response variable. Okay, so I need you to predict the number of the final score for students with 0 absences. Then I'd like you to predict the average final score for students with 3 absences. Okay, so I'll go quiet for a minute, and as soon as you do it, as soon as you get those calculated, put them over there in the chat for us, okay? Darn it, I had my thing on mute. My apologies. Thanks for letting me know, Julia. All right, let me go back here. I hate it when I do that. Okay, so let me go back here a little bit. Okay, so alrighty. So we did the 4 absences, right? So 79.7865. Okay, and then Sarah was asking about 4. How did we know 4? Well, I just chose 4 to help us practice with it. We could have chosen any number there. Does that make sense, Sarah? I was just choosing a number to practice with. Okay, all right. So, okay, so then a few of you guys got the one for 0 absences. And, you know, if you've studied algebra recently, uh, you might know that actually we don't have to do any arithmetic at all. If we put in 0 for x, then we're on the y-axis, right? So it's just going to be the y-intercept, right? So it's y equals mx plus b that's going on here. But let's push through the math anyway and just verify that. So if you put in 0 for your explanatory variable, then that piece goes away and you're left with the y-intercept. Okay. And so what am I referring to? Y equals mx plus b. So let me just write that up here. Y equals mx plus b. You might remember that from your algebra days. B is that coefficient out there. That's the y-intercept. That's where it's hitting the y-axis. Yes? Okay. So good. That's the prediction for 0 absences. Okay. Now, the 3 absences case, let's see here. So yeah, that does look correct to me, 82.5026. A couple of you guys have that. So let me write that down and then we'll verify it. And then there's a super important takeaway from moving from 3 to 4 absences. Okay, so let's do one more of these predictions. Okay, so we're going to go negative 2.7161 times 3 plus 90.6509. Okay. And by the way, I want you to be impressed by that, right? I mean, this is one of the great things about this linear regression technique. You can make these really nice predictions, right? If you have a good model with a strong correlation, you can make these really accurate predictions. Okay, so 6509. So yes, 82.5026. All right, so everybody feeling okay about that? So that's how we can use the regression equation to make predictions. And that alone, that by itself is also very important. The next thing I want to think about to help us interpret the slope is this difference between 3 and 4 absences. Okay, so for the 4 absences, it was 79.7865. For the 4 absences, I'm sorry, for the 3 absences, it was 82.5026. Okay, I want to subtract those numbers. Why? Well, we're going to get a number that is familiar to us. 7865. What is that number there? You guys see that? Negative 2.7161. That's nothing but the slope. Yeah. So what happened? When we went from 3 absences up to 4 absences, we had one additional value for the explanatory variable. Okay, so the explanatory variable increased by 1 unit and the y variable changed by the slope. Okay, so that's actually what we call the unit interpretation of the slope. So let's write that down. Okay, you're going to see this on the final. Okay, so you need to know how to write this out. Okay, so here we call this the unit interpretation of the slope. Okay, unit in math means 1. Okay, so when we change the explanatory variable by 1, then the change in the y variable is equal to the slope. Okay, so here's what it says. As for each additional absence, okay, so for each additional absence, on average, we expect the final score to decrease because it's a negative slope, by about 2.7%. Okay, so if on the final, when I ask you to interpret the slope, you're not going to say rise over run. That's true, it is rise over run, but what we're trying to do is get more insight into the relationship between the two variables, right? And so this is about as much insight as you can get, right? For each additional absence, we expect the final exam score to decrease by about 2.7%. Okay, so that's super important, right? And so that's another thing I want you to be impressed by with linear regression. I just don't think you can get a more precise description of the relationship between those two variables than that. Okay, let me draw you a picture above. Okay, so we have slope, right? And this time, let's make the triangle a little bit smaller. Let's just increase the unit by 1. Okay, so we have our triangle here, we have our run, and we have our rise. Okay, so with the unit change in the x variable, we're only going to let the run be 1. So we're going to increase by 1 absence, right? From 3 to 4, from 8 to 9, 9 to 10, whatever, right? So if we let the run be 1, what happens to the rise? Okay, so let's come back over to our equation here. So we have rise and we have run. The negative 2.7161 is not a fraction, but I can turn it into a fraction by putting it over 1. Okay, so now we've let the run be 1, and what's going to happen to the rise? Well, the rise is simply going to be the slope. Okay, so this is the unit interpretation of the slope. We let the run be 1, and then the change in the explanatory variable will be the slope. Okay, so for each additional change, unit change in the explanatory variable, then the slope will tell us how much we expect the response variable to change by. Okay, so very, very important takeaway from linear regression. So that's our interpretation of the slope parameter. Then we want to do the same for the y-intercept. That's also interesting. Okay, so what is the interpretation of the y-intercept? Well, let me clean up the graph here a little bit. What is the y-intercept? The y-intercept is where the x variable is 0. Okay, so the GeoGebra graph is a little bit misleading here. The x-axis is actually over here, right at 0, right? The y-axis, right? This is the y-axis here. Okay, so that's the y-axis, that's the x-axis. When you have 0 absences, you're back over here on the y-axis. Okay, so when we put in 0 for the x variable, then the expected output is the y-intercept, right? So that's our 90.6509. So in some cases, the y-intercept also has a nice interpretation. What does it mean? Well, for students with 0 absences, we expect the final score to be about 90.65, or about 91%. Does that make sense? Okay, so when you're asked to interpret the y-intercept, you put 0 in for x, you get the y-intercept, right? And you say, well, that's the expected value for the case where the explanatory variable is 0. Okay, so this is called the interpretation of the y-intercept. Also very important. And you'll see this on the final too. The interpretation of the y-intercept. Okay, so for students with no absences, the expected average final grade is the y-intercept, which in this case is about 90. What do we round to? 1, 2 is fine. So maybe we'll just go to 2 decimal places there. Okay. Great. It doesn't end there. There's more stuff, okay? We're just getting started. So let me just pause and see if you guys have any questions here about anything we've talked about. I know it's quite a lot, but regression is, there's just so much to it. Anything else? Okay, so something, just a little quick tip about GeoGebra. GeoGebra can actually calculate these outputs very quickly. If I come back over here, if you look down at the bottom, if I put in 0 and hit enter, do you see how it automatically creates the output? So if I put in 3 and hit enter, it automatically creates those values. So when you're doing the homework, you can use that if you want. Make sure you know how to do that by hand. It's not hard, right? But if you want to save some time, you can do that. Okay. So what next? So let's go back to our notes here. So we've talked about the least squares regression criterion. Okay, we've talked about interpreting the slope and the y-intercept. Okay, so the slope describes the estimated difference in the y variable if the explanatory variable for x happened to be 1 unit larger. Okay, so we call that the unit interpretation of the slope. Then the y-intercept describes the average outcomes of y if x equals 0. Now note that not every data set would make sense for x equals 0. Okay, if x is, say, weight and y is height, you're not going to have anybody with 0 weight, right? So while the slope almost always has an interpretation, sometimes the y-intercept won't have a physical, concrete interpretation. We'll see more examples later. Okay, so 2 other things. You want to be careful with extrapolation. Extrapolation is where you follow the line beyond the data set. Okay, so the linear regression tends to work pretty well as long as you're making predictions that are close to your data set that you use. But if you start making predictions that go too far out of the pack of the data, then you're doing what's called extrapolation, and it's kind of risky. The last thing we need to mention here is this coefficient of determination, and this is quite an impressive thing too. It's also called the R-squared, and what it gives us is basically a grade. I think of it as like a grade for the model. Okay, so like a grade you would get in a class. That's what the coefficient of determination is, but for the model. So it's a more common way to explain how good the model is. So I think of it like a grade. Okay, so let's go back to our example here with the grades. Okay, so how good is this model? Okay, so so we have this data set, right? And it's clearly decreasing. And so let me add on some stuff here. So for this coefficient of determination. You can think of it in a couple different ways, right? So it's a grade for the linear regression model, okay? And it tells us basically how much the model explains. So how much does the model explain? Right? I mean, that's why we do studies, right? We're trying to explain something. In this case, we're trying to explain why not every student gets the same grade in the class, right? So if we look at the scatter plot, some students are doing well, other students are doing poorly, right? And some students are kind of in the middle. So I've got a weird question for you. Why doesn't every student get the same score? That's kind of what we're trying to answer, yeah? We're trying to explain why there's this variation in scores, okay? So if everybody got the same score, what would it look like? Well, it would basically just be a flat line, right? If everybody got the same score, it would look like a flat line there. Okay, and that would be good if if everybody got the same high score, right? But that never really happens, right? We always see some kind of variation. So why doesn't every student get the same score, right? In other words, why is there variation? Okay, and so we can think of the purpose of this study is we're trying to answer this question. Why is there variation in the exam scores? Why does it start high and go low? Well, there's lots of possible reasons. Let's think of some possible reasons. Okay, so here's some possible reasons. Okay, maybe some people like math more than others, right? Okay, so maybe some people are just more interested in the topic, right? Some people actually really enjoy their classes, right? Sometimes, right? Yeah. Other people hate them, right? And so maybe, maybe people are just more interested, that's why they do better. Other people are less interested, that's why they don't do as well, right? So maybe interest has something to do with it, okay? Maybe some people spend more time studying, right? So we could think about study time, okay? Maybe the people doing better put more time into studying, and the people who are doing worse put less time into it. It's possible. Yeah. Anything else? Yeah, there's lots of reasons, right? Maybe there's background preparation, right? Some students in this class come in, they just finished high school. Maybe they took AP, statistics in high school or something, right? And they're really strong with math, and maybe they just have a stronger background, and that's why they do better. Yeah, there's all sorts of reasons. What we chose in this study was absences, right? So in this study, we said maybe it's absences. That's what's causing the variation. Okay, so what we do with the coefficient of determination is we basically see how much of this variation can be explained by one variable, and that variable is absences. Okay, so how much can be explained by absences? Okay, so that's what R squared tells us. Okay, so the formula is pretty amazing. We're not going to go through the formula. It's basically just R squared. So I'm going to take R. We calculated that earlier. Where was R? We found R to be negative 0.9539. Okay, so negative 0.9539. Okay, so we're going to square that. That's where the term R squared comes from. That's how we calculate the coefficient of determination. Okay, so I'm going to take that R value and I'm going to square it. So I go 0.9539 negative. Of course, when we square it, it goes positive. And so we go 0.9099. Okay, and this might seem a bit like magic, but it's true that what this tells us is that absences and absences alone explain about 91% of the variation in scores. Okay, so let's write that down. That's super important. Okay, so what we can say here is that absences, that one variable can explain about 91% of the variation in exams in final score. Okay, so think about that. Um, that's that's pretty good, right? If you get a 91% in this class, then you did well, right? You get an A minus. That's great. Okay, so basically this model is getting a good grade. This one model explains 91% of the variation in final exam scores. Okay, so it doesn't explain everything. There's still about 9% left to be explained. And who knows, maybe these other variables up here can explain that remaining 9%. But if you can explain 91% of something, you're doing pretty well, right? So as a researcher, if you can explain 91% of something, then it's probably a success. So in other words, this is a good model. Does that make sense? So it's kind of a harder thing to understand and wrap your mind around, but once you get it, then you realize this is super important, this coefficient of determination. It's almost magic that you can actually tell people how much that the model explains. Okay, so there we go. That's a lot, right? There's a lot there, um, but that's regression. It's kind of complicated. So any questions there about those? Good. Let's see here. Can you go over again how you got R? Yes. So R comes from a formula, okay? But we don't actually use the formula in this class. We used to, but we took it out so we could put other things in. So instead of using the formula, we use GeoGebra, okay? So let's go back through how we get R. Basically, you highlight the data, you hit the two variable regression analysis, then you hit the sigma x, and there's R right there. Does that make sense, Killian? Does that answer your question? So R is right here, negative 0.9539. Great. So you calculate R using software, then you square R. It's actually right here, the R squared, 0.9099. And so if you work in a field where there are analysts who are calculating these linear regressions, this becomes a quick way of basically telling people how good your model is. Okay, so you come up with a model, your colleague comes up with a model, somebody from another institution comes up with a model, everybody gets an R squared, and then you publish your results, and then this guy's got a 91% R squared, you've got an 87% R squared, right? And then it's just a nice way of kind of seeing how good various models are. So it's like a one number that we can use to tell quickly if a model is good or not. So very, very important idea there, the coefficient of determination. Okay, so we did the slope. So let's see here. Let's see here. So when the number of absences increases by 1, the grade in the class decreases. And then, yeah, we did the intercept. Good. So all done with that. Let's actually do the example in the lecture notes now. Okay, and I'd like you to try this one. We've got about 20 minutes, and I think that would be a nice place for us to kind of conclude the week. So here on page 180, we have a new problem, a new data set, and that's how it is as statisticians. It's always a new day, a new data set that you're investigating. This time, we're looking at two variables that at first glance seem completely unrelated. So we're at the level of the neighborhood. Okay, so every neighborhood is going to have two things. Okay, we're going to collect two pieces of information about every neighborhood in our sample. we're going to somehow measure the percent of people wearing helmets. Okay, so sometimes you get these data sets and you wonder like how on earth do they actually collect the data? But you know that's part of the fun of being a scientist. Um, so so they have some way of estimating the percent of people wearing helmets when biking. Okay, for the neighborhood. Then they also have a way of estimating the percent of children receiving reduced fee school lunches. That's probably a little bit easier to collect, right? Um, so what's a reduced fee school lunch? It's a cheaper lunch, right? It's an easy, so it's like a subsidized lunch. So, you know, if you've got a kid in school, then if you get a reduced fee lunch, it just means less expensive, right? And so every child will either get this or not, right? So we have some percent of children getting the reduced fee lunch for the neighborhood. So every neighborhood has two numbers, okay? So for example, this neighborhood here, about 20% of the kids were receiving reduced fee lunch, and about 22 or 23% of bikers were wearing helmets when they were biking. Okay, so I know it sounds kind of um, kind of wild, right? Trying to relate these two variables. But if you look at the scatter plot, there does seem to be a downward trend there. And so, and this came from a real paper, by the way. This is a real study that was done. Um, so, there is a trend there, and we created the equation. Okay, so this is the least squares regression equation. So you don't have to go to GeoGebra here. I'm giving you the output. So we have the equation, and we have R. Look at R. That's actually pretty strong negative correlation. It's not perfect, obviously, but pretty close to -1. So it does appear that there's a negative, pretty strong linear relationship here. So what I want you to do is to take these two facts here about about the linear regression and R, and I want you to interpret the slope and the y-intercept. Okay, so basically fill in the blanks here in the lecture notes. And then if you have time, also calculate r squared. What's r squared? That's the coefficient of determination. Okay, so give those a try. I'm going to go quiet for a few minutes, and then I'll come back. And if I forget to unmute myself again, please let me know as soon as you can. And yeah, we'll be in a good spot. This 6.3 section is really thick with a lot of ideas. If we can get through 6.3 today, then I think next Tuesday when we come back, we'll be in a good spot to pretty much finish everything. So, so I'll go quiet for maybe 4 or 5 minutes and let you guys work on this. We'll come back together at 12:36, 12:37. Okay, so I'm not asking you to come up with the equation, it's already there. I'm not asking you to find R, I've already given it to you. What I'm asking you to do is to interpret the slope first. Okay, so don't say rise over run. Okay, it is rise over run, but we want to go deeper than that, right? We're trying to understand how reduced feed lunches impacts wearing helmets, right? So it is rise over run, but it's one particular kind of run. Okay, so we're going to put the triangle in here. There's our run, and here's our rise. Okay, so slope, or M, equals rise over run. Okay, and so the slope here is this number. Okay, so it's mx plus b, yep. So we have negative 0.537. Negative 0.537 isn't a fraction. So what's the run? Well, we can always put a 1 under it to make it into a fraction. So if I run 1, then the rise actually becomes the slope, right? So the rise is that value there. So can anybody put that into a sentence for us? When something increases by 1 unit, then the other thing is going to increase or decrease by some value. Any ideas here? It's a little bit harder to understand than in the grades and absences. That's why I did the grades and absences value problem first. A little bit more obscure, I think, but still interesting. Anybody want to go out on a limb there? So, well, the X variable is percent of students receiving the lunch. Let's see, I do have a comment here. Good, yeah, good. That's the first part, yeah. Children receiving reduced fee lunch, right? So the rise variable is helmets, right? So we have percent helmets on top. And then for the run, we're going to have percent with these reduced fee lunches, right? So yeah, when the reduced fee lunches increases by 1, the percent of people wearing helmets when biking is going to decrease by almost 0.5%. How do you know where to put the triangle? There's not really a right or wrong place to put it. In fact, once you get the hang of it, you don't even need to draw a triangle. I'm just kind of doing that visually to help you see the slope. Yep. You don't even really need it once you get the hang of it. The slope is always going to be the change in the response variable. Good. So when children receiving reduced fee lunch increases by 1 unit, which in this case is a percent, okay? So when it goes from 20% kids on reduced fee lunch to 21% reduced fee lunch, for example, then this model predicts that the people wearing helmets when biking decreases by 0.537% on average. Okay. And this came from a real study. So basically, what's the story going on here? This is about household income, right? So to get the reduced fee lunch, you have to have some kind of, there's some kind of maximum, household income you can have, right? So if you're in a neighborhood here where there is a large percentage of people or kids on reduced fee lunches, it's easy to imagine, well, if you're having a hard time paying, for your kids to have lunch, right, at school, maybe you're not going to go out and buy, a helmet, right? Does that kind of make sense? So they're looking at these two variables. Yeah, one's not really causing the other, but we do see a pretty strong relationship there. Okay, good. What about the y-intercept? So that's the slope. That's the unit interpretation of the slope. The y-intercept is back here where the graph hits the y-axis. Okay, so that happens when your explanatory variable is 0. Okay, so if you're in a neighborhood where no kids are receiving reduced fee lunch, so it'd be like, kind of a wealthier neighborhood, right, where nobody is qualifying for that reduced fee lunch. What happens to the percent of people wearing helmets when biking? Well, it's actually the y-intercept. Yeah. So we don't even have to put in 0. We know it's just going to be that number right there. So the average percent of people wearing helmets when biking when no children are receiving the reduced fee lunch is that 55.34%. Okay, good. All right, so you'll have to do that on the final. You're going to have to interpret the slope and the y-intercept. And you have to go beyond, like rise over run. Okay. Then we want to see how good the model is. And that's what the coefficient of determination does for us. So R squared is just a fast way of saying coefficient of determination. Sorry. That's what R squared is. Okay. And you literally just have to square R. So we're going to go 0.849. We square it. It becomes positive, and we get 0.721, okay, or about 72%. So in other words, 72% of the variation in helmet wearing can be explained by the model, by the percent of people, percent of kids receiving reduced fee lunch. Okay, so 72% of the variation in people wearing helmets when biking can be explained by the least squares regression line, or we can say the model, or by the x variable, the explanatory variable. Okay, so it's not as good as the other model, but it still does explain, a solid majority of what's going on here. Okay, so if you get a 72 in the class, you get a C, so you're passing, right? So it's not a terrible model there. So there we go. Okay, but so there's still like 28% of the variation is left to be explained there. All right, great. So super important ideas there. We've got 5 more minutes. Let's go ahead and have a look at 6.4. The more we get done today, the better for next week. Are there any questions on this problem here? Okay, so we talked about outliers back in chapter 4. That was for single variable data, univariate data, right? We had the fences, the upper fence, the lower fence. We have a similar idea with linear regression, but it's more complicated because it's two-dimensional data. We're going to look at outliers in linear regression. And what we'll see is that linear regression is very sensitive, or it can be very sensitive to outliers. So we need to treat these very carefully, and we need to be aware of what they can do to the linear regression. Okay, so some outliers can really change the model very quickly. And so those points are called influential points because they can influence the model. Okay, so an outlier that appears to invoke its influence on the value of the correlation coefficient or the slope of the model are influential points. And so when we're making one of these models, we have to be very cautious. So how do we handle it? Well, some people say, let's just take out the outliers and run the model. Other people say, well, that's kind of cheating because, the outliers are real data points, so we should leave them in. Some people say, run the model twice, once with the outliers, once without the outliers. Okay, and everybody agrees that if you have an outlier, you should see if it came from an error, right? Sometimes outliers come from errors. So if it's coming from an error, then you can take it out. But I tend to think let's run the model twice, once with the outliers, once without the outliers, and see what happens. And that's what we're doing here. So here on 181, we have a data set. Okay, so we have a scatter plot, and it's clearly a downwardly trending relationship and more or less linear. And we've calculated the regression line. So we're giving that to you. You don't need to calculate it in this problem. We're giving you R, so negative 0.7, so fairly strong relationship, negative. And so what we do here in these other graphs are two basically thought experiments. Okay, so just some hypotheticals. Very useful technique in education, right? You get an example and then you add in a couple of hypotheticals to it, right? So let's imagine that this data set actually originally had this outlier over here. Okay, so we're going to ignore case 2 off to the right. We're just going to consider this case in the middle. So let's say so we fit the model, and then we realize actually there was this outlier. What would happen to the regression if we had this additional outlier? Okay, and you'll also have something like this on the final. So you'll have your regression, and then you'll have an outlier, and you'll be asked about what the outlier does. What is its effect on the model? Does it make the model stronger? Does it strengthen R? Does it make the model weaker? Does it reduce the effect of R? Does it change the slope? Does it make it steeper? Does it make it flatter? These are the kinds of things you'll have to answer on the final. Okay. Unfortunately, we're a little bit out of time today, so we can't really investigate this one too much further today. So what we'll do next week is we'll come back in on Tuesday, and we'll just kind of start at the beginning of 6.4. So we're in a great spot for Tuesday. I think we can knock out all of chapter 6 on Tuesday, and then probably that Thursday we'll be able to spend almost the whole time reviewing. Okay, so any questions here as we go into Thanksgiving break? Anything I can help you guys with? All right, so just 2 more classes after Thanksgiving break. And then, yeah, so have a good break. Hopefully you can take some time off and relax, and then we'll come back and have our last week of the semester. Okay, well, take care. See you guys next Tuesday. Thanks, everyone.